Hello guys, good afternoon. So guys, today we are going to understand a concept here which is required to find out the optical nature of a compound, right? Optical nature of a compound, and that's the basic condition for a compound to show optical activity that we have already discussed, that the molecule is unsymmetrical, means there's no any kind of symmetry present into it, right? That's the condition we have. So how do we find out that in a given molecule there is symmetry or symmetry exist? In a given molecule, symmetry exists, correct? So that is what we are going to discuss today in this session. And the elements, this we call it as sorry, the elements of symmetry, correct? So what are the various different types of symmetry we have that we are going to understand today in this section? Okay, fine. So elements of symmetry. Symmetry is what? If you say this, symmetry is anything by which a given molecule can be classified into two identical components of it. Okay, so what is symmetry? Symmetry, basically it is a property of a molecule. Okay, it is the property of a molecule by which any molecule can be divided into two equal halves. Two equal halves which are identical and mirror image of each other. That's how we define symmetry. Okay, identical and mirror image, these 2 points are important here. Like I said, identical and mirror image is important, right? This you have to keep in mind. This is the symmetry we have. A given molecule is said to be a symmetrical molecule which can be divided when it can be divided into two equal halves, right? Or we can say two identical halves, and each halves are mirror image of each other, right? That is the symmetry we have. What kind of symmetry? See, actually, a given molecule, like last class we have discussed about optical activity of the compound, and if you remember, we talked about chirality. Okay, chirality. So there I said that the molecule must be chiral in nature to to show optical activity. That is a condition for a molecule to show optical activity. How do we define chirality? Chirality is a property of a molecule by which it cannot be divided into two equal halves, right? And this thing, the chirality property, we can understand with the elements of symmetry. Okay, So I haven't discussed this symmetrical part over there because this is not that much important for KVPY level, and that's why I'm making a video out of it, right? So basically, you should know a little bit of idea that how do we find out symmetry. So we'll do all these symmetrical elements in detail over here, but all these things are not, you know, all the things I'm talking about. It's not like it is not at all required. All the things is not required for KVPY, okay? But if you go through the video once, you will have the understanding of symmetrical elements, and you can easily identify the symmetry, whether it is present or not in a given molecule, okay? So obviously, you don't have to put much brain into it, but yes, you should know the facts, so you should go through it once, okay? So there are various different types of symmetry present we have here in the molecule, and this we call it as elements of symmetry. Elements of symmetry. So we have four different types of elements of symmetry. We have plane of symmetry, we call it as POS. The second one is center of symmetry. We call it as COS. The third one is axis of symmetry. We call it as AOS. And the last one we have is alternate axis of symmetry. This four kind of symmetry present in a given molecule. It's not like all the four types present all the time, but these are the four types anyone can present in the molecule, more than one also possible in a given molecule. Now for your exam, whether it is IIT JEE, NEET or KVPY, the first two are important. Right? Mainly most of the questions comes from these two parts only. This is the least important we have, alternate axis of symmetry. Okay, AAOS. So today in this session, we are going to study plane of symmetry, that is POS, POS. Okay, so let's start with the plane of symmetry. Heading, all of you write down. Plane of symmetry, POS. What is a plane of symmetry? It is an imaginary plane. Same thing, only we have a plane over here. It is an imaginary plane which divides the molecule into two parts. It divides the molecule into two parts, and both parts are identical and mirror image of each other. And mirror image of each other. That is the plane of symmetry. Let us try and understand this. What is a plane of symmetry? How do we identify it? Okay, let's a cyclopropane. Okay, an example of cyclopropane. Or if you take a cyclobutane, okay, or you take a circle, or if you take a pentagon, right, or any other such structure. Okay, so if you see in cyclopropane, easily you can identify there is a plane of symmetry passes through this line. This is the plane of symmetry we have. Okay, because if you cut the molecule like this, it will be into two equal half. One half is this, another half is this. Here also we can have plane of symmetry like this, right? You can also think of another plane of symmetry which passes diagonally. This is another plane of symmetry we have, and like this in circle, we can have so many plane of symmetries which passes through the center, right? Actually, infinite number of plane of symmetry possible we have. Okay, I'm just drawing a few over here. But there are infinite number of such plane possible which divides the circle into equal halves. Okay, so what are all these? First of all, this is a POS, plane of symmetry. These are also POS, plane of symmetry, and these are POS, plane of symmetry, right? Right, infinite plane of symmetry possible here in case of a circle. Okay, if you analyze this, the two equal half, each point has mirror image into this one. Consider here we place an mirror, then each point, you see this point has a mirror image this side, this point has a mirror image this side, okay, this point has a mirror image here. So like this we have each point has mirror image. Similarly here also we can say we have mirror image, each point has a mirror image here, right? So these are the plane of symmetry, right? So an imaginary plane which divides the molecule into two parts and both parts are identical and mirror image of each other, right? Two parts, right? Both parts are identical and mirror image of each other, called plane of symmetry. So actually this is not that much difficult to understand, but actually you need to visualize this, you need to imagine this structures, and then you can imagine the plane also, right? Since we're talking about a plane, it is not a line. Okay, we're talking about a plane. So you have to imagine this. That would be a bit difficult, you can say here, but however the portion is not that difficult. Okay, so when you solve some questions, you will have the understanding of it. And how do we identify the plane of symmetry in a given molecule? Let us discuss some letter and plane of symmetry into it. So for example, suppose I take a letter which is A, right? In this letter A, we have a plane of symmetry. Along this line, we have a plane of symmetry. Letter B, we have a plane of symmetry along this line. Letter C, right? D, E, F, G, H. Okay, like this we can take many. N, for example, M we can take M, we can take N, O, right? P, Z, all these letters you see. In all these letters, what happens? We have a plane of symmetry here, a plane of symmetry here, a plane of symmetry here, a plane of symmetry here. F does not have any plane of symmetry. Z won't have any plane of symmetry. We have a plane of symmetry here. M will have a plane of symmetry here. N, we don't have a plane of symmetry, right? So we have no POS. I'll just correct it. So no POS here. Here we have infinite number of POS possible. We have already discussed it as in case of circle. P, we don't have plane of symmetry. Z also, we don't have plane of symmetry into this. Okay. If you see this, you can understand, you must be thinking of, if you take an example of this letter that is N, you must be thinking of a plane of symmetry. And a plane of symmetry passes through this line like this, right? So we are getting identical part here. Means this part and this part, obviously the length of this part will be same. This has the same length actually. That is understood. Okay, please consider that. So obviously this is identical, right? This part and this part is identical, but they are not mirror image. If it is mirror image, you see, then this part should have the mirror image. Suppose this point, we are getting the mirror image over here, right? But what about this one? For this point, we don't have a mirror image here. For this point, we don't have a mirror image here, right? So that's why the two parts are identical, but no mirror image into this one. No mirror image, and hence this does not have any plane of symmetry. Same thing is true for Z also. It is like if you rotate anti-clockwise, you'll get Z. This is the same thing we have for Z. So this is the plane of symmetry we can have. Okay, and we can understand plane of symmetry like this. So I have taken the basic example to make you understand what is plane of symmetry and how do we identify it. But in the question, you need to understand this to find out the plane of symmetry in the molecule. So in molecules, how do we check the plane of symmetry here? That we'll understand now. Okay, so to understand plane of symmetry in the molecules, there are 4-5 different types we have in which we can understand different things. So the first type we are going to discuss molecules here. Molecules, and we are talking about, in the first case, we are talking about unsaturated molecule. Unsaturated molecules. Unsaturated molecules are those molecules in which we have double bond present. Okay, mainly we are talking about double bond here. Okay, just a second. Okay, unsaturated molecules. For example, you see, I am taking a simple example here, and that is ethene. C double bond C, H and H. Here also we have H and H, ethene. So easily you see, if you divide the molecule like this, You'll get two identical molecules and mirror image also. This carbon, carbon, hydrogen, 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 mirror image. And similarly, we can divide the molecule like this also into two equal halves. Okay, so we have two plane of symmetry possible here. Sometimes they also ask you the number of POS possible in the molecules. Okay, so one is this, other one is this. Okay, this is one thing. Now you see this molecule is planar. It is a planar molecule. And this is present in a plane in which the plane here is the plane of the molecule because the carbon atom is sp2 hybridized, so it is trigonal planar. So you can consider this molecule is along the plane of the paper. You have drawn the molecule, so along the plane of the paper the molecule is present. Or suppose in the board, if I draw this, so the plane of the board that we have is the plane of the paper, the plane of this particular molecule, right? So if you divide the board into two equal halves, it's not like from in between like this. You have suppose the edges of the board like this, and if you cut the board like this, so that half part will have here, that side half part will go away from you. Like you can understand this when you slice a braid in between, right? So you have a braid, when you slice it completely half, like you get two equal halves here, not along this plane, not like this, not vertical, but horizontal if you slice the braid. Okay, so if you take two equal halves, right, so that plane, the plane of the braid is the plane of the symmetry. We have one plane of symmetry here. So any planar molecule will have at least one plane of symmetry, always. At least one POS. At least one plane of symmetry POS, and this plane of symmetry, and this is the plane of the molecule, of the molecule. We'll have at least one POS, and this is the plane of the molecule. Correct? That is always true. At least one POS will be there. Right? Others we can think of, like one is this always along the plane of the molecule. Right? Half part will be on the back side, half part on the front side towards you. Right? That's how we have it. So this is the planar molecule. Now suppose if I replace the hydrogen with any other element, like so total number of planar symmetry, if I ask you here, the total number of planar symmetry, if I ask you, is total POS. So 2 we have already, right? Here we have 2 plus one more we have, that is total 3, and this one is the plane of the molecule. Plane of molecule. Obviously we cannot show this. So here 2 POS I have shown here, that's why I have written it 2, but total it should be 3, and I will show you the third plane of symmetry also. The third plane of symmetry would be a plane that passes through all the atoms here in the molecule like this. Means if you cut along this plane, the plane I am drawing now, if you cut like this, you'll get half H on the bottom, half H on the top, and here half carbons on the top, half carbons on the bottom, and we'll have a plane like this. This entire plane is the third plane, which is the plane of this molecule. The total plane of symmetry would be 3. Okay, so whenever you have a planar molecule, it must have the plane of symmetry with it, right? The plane of symmetry with it. Okay, sometimes they ask you to find out the number of POS present, right? To identify the optical activity, you just need to know whether the plane of symmetry is present or not. Okay, there you don't have to count the number of a plane of symmetry present. To identify whether the molecule is optically active or not, just you need to know whether we have any kind of symmetry present or not. With number of symmetry elements, it is not at all related. It's just related with the presence or absence of symmetry. Okay. So to identify optical activity of any compound, you just need to check the symmetrical elements present or absent, right? Number of symmetrical element, you don't need to count for that. But specifically, if they ask you how many planar symmetry present, then you need to consider all these factors. Okay, and that's why I'm discussing this. Some more examples we'll see. Suppose we have a molecule C double bond C H Cl H and Cl, right? So could you tell me here, if you think of it, we have a plane of symmetry like this. You can think of a plane of symmetry like this. H mirror image, chlorine mirror image, carbon mirror image. But this one is not a POS, a plane of symmetry, because this is not the mirror image. This is not the mirror image. So we have only one plane of symmetry plus one more we have along the plane of this molecule, this one, along the plane of the molecule. So total number of symmetrical plane of symmetry, if you ask me, the answer for this question is, one is this, another one is along the plane. There is total 2 POS possible here. Okay. Similarly, if you think of this one, C double bond C HCl HCl Br and I. Okay. So this one we cannot have, this one we cannot have. We have only one plane of symmetry here, and that is the plane of the molecule. To understand this, you can assume all the atoms as a sphere, right? And when you cut this molecule along this plane, we have half a sphere this side, half a sphere other side, right? That's what you can understand. So we have here one POS possible for this. Okay, could you tell me the number of POS present in this molecule? Okay, this one. In this also easily you can understand, we'll have a plane of symmetry along this line. You can cut the molecule like this. Each point has its mirror image. Okay, so one POS is this. Another one is again the plane of this molecule, right? So we'll have total 2 POS possible into this one. Right, along this plane. So along this plane, we can have a plane of symmetry and total 2 POS here. So always remember that any planar molecule will always have at least one POS, and that POS is the plane of the molecule itself. Okay. Now, one very important example we have under the saturated molecules only, and that is cumulines. Cumulines, we also call it as allenes. Allenes. Allenes are the compound which contains continuous double bond, one after the other, C double bond C, double bond C, like this, okay? Double bond C, double bond C, and so on. This is cumulines, okay, or allenes we call it as, where on this atom we have certain groups or atom attached to it, okay? So here we are going to talk about two types of allenes, one in which we have even number of double bond, for example, C double bond C, double bond C, even number of double bonds, and another one we are going to discuss here when we have odd number of double bonds, C double bond C, double bond C, and double bond C, odd number of double bonds. Okay, so if you see here, the elements or groups attached to this carbon atom, we have this side we have P, suppose here we have Q, here we have R, and here we have S, P, Q, R, S. Okay, this one is also suppose R, PQ. Okay, now here you understand when you have a double bond here, then the molecule is what? Then the molecule is non-planar here. Okay, if we have even number of double bond, okay, see, few things you should know for this kind of questions. Okay, we can discuss about it, why it is non-planar and all, but for that you should know the understanding of orbital overlap. Okay, you can consider px, py, pz orbital here. You find out it will be in xy plane or it will be in yz plane. So it is in a perpendicular plane actually. Okay, so those things I'm not going into the detail of the orbital overlap here. Two things you have to keep in mind here. The first thing is what? That this bond RS, one is going into the plane, and other one is coming out of the plane like this. Out of the plane like this. Okay, so these two are what? You should know these two atoms are perpendicular to each other, and these two are perpendicular to the plane of the paper also, in which you have drawn. This P and Q is present in the plane of paper. Present in the plane of paper. This you should know. Okay. Okay, orbital overlap and the concept I'm not discussing now because we haven't done the concept of, how the orbital overlaps and forms a bond. Okay, that's why I'm skipping that part. But that is also there for understanding. If you keep these two things in mind, you can do the questions easily. Okay, now when you have even number of double bond present, then the molecule is what? Molecule is non-planar. Molecule is non-planar, and this can have different number of plane of symmetry depending upon the atoms or groups attached to the terminal carbon, right? So what happens here, you see, non-planar it is, this won't show GI, I'll do that later. If three conditions we have P is equals to Q and C equals to D. P equals to Q and C equals to D. Then we have two plane of symmetry possible. if P equals to Q and C not equals to D, or if P not equals to Q and C equals to D. Any one of this condition, we have one POS possible, and if A not equals to B, and sorry, not A, we have PQ here. If P not equals to Q and R not equals to S. Why I have written here C and D? Okay, because I have written in my notes at C and D. Here also I've written C and D, not this one. So it should be PQ, R equals to S here, R does not equals to S, and R equals to S. So if this condition we have, then there is no plane of symmetry present. No plane of symmetry present here. So these three conditions we have that you should keep in mind, and then you can find out the plane of symmetry. See, if all four are equal, right? If all four are equal, then we can have a plane of symmetry along this line and this line, right? P equals to Q and R equals to S. So we can have a plane of symmetry like this, and we have a plane of this, not this one, because this P and R maybe may not be equal. Okay, if all are equal, P is equals to Q is equals to R is equals to S, then one is this, another one is this, and another one is the plane of the paper, right? That is the third case we have here, right? But here what happens, you see, since the molecules is non-planar, then we cannot consider the third type of plane of symmetry. Non-planar, so we cannot consider the plane as the plane of symmetry. So that case I am eliminating here. So here we have the plane of symmetry. P is equals to Q, R is equals to S. One plane of symmetry is this, and one plane of symmetry is this. P is equals to R and Q is equals to S. Okay, if P is equals to Q and R is not equals to S, right? P is equals to Q and R is not equals to S. Then what is the plane we can say? We can consider a plane which consists of these three elements, R, C, and S. The plane belongs to these three elements. This is the mirror image we have. And similarly, we can have another condition, these three elements, and we'll have a plane along this line. Correct? Another one, if all these four are not equal, then we won't have any plane of symmetry into this. And this is the condition of optical activity. Means if you have even number of cumulines with all different groups attached to it, then the compound is said to be optical activity. One very important property of this won't show GI. No geometrical isomerism we have, but if this condition is true, P not equals to Q and R not equals to S, R not equals to S, then we do not have no plane of symmetry, and hence it is optically active. So this molecule can show optical activity if this condition is there, P not equals to Q, R not equals to S. Okay, molecule is non-planar, you see it is in X, these two are in the perpendicular plane. Okay, that's why if these two are equal also, P is equals to R, R is equal, Q is equals to S, then only there won't be any plane of symmetry, right? Because those molecules are in different plane. Okay, now when you have odd number of pi bonds, okay, non-planar for even pi bonds, Even pi bonds, cumulines are non-planar. Simply you can sum up this. Even pi bonds, non-planar, no GI, show optically activity if these four groups are different. If you have odd number of pi bonds present, then it is planar. It is planar molecule. Odd pi bonds we have. Odd pi bonds, it is planar. And in this also, all these are planar, right? So obviously we'll have a plane of symmetry along this line. We'll have a plane of symmetry along the plane of this molecule. Right, this plane we have a POS. This is a POS, we have plane of symmetry. Right, so we obviously have a plane of symmetry, and hence plane of symmetry is present, it won't show geometrical isomerism. Okay, but if plane of symmetry is there, the total number of plane of symmetry we count here. In the first case, if we have P equals to Q, P equals to Q, and R equals to S. P equals to Q, R equals to S. So we have a plane of symmetry like this, right? And one plane we have this one already. So one is this one already we have here. So in this case, we have two plane of symmetry possible. Okay. The second one, if we have P is equals to R and Q equals to S. P is equals to R and Q equals to S. Then also we have two POS possible, right? One is this and another one is this. Third one, we have if all four are equal. P is equals to Q is equals to R is equals to S. Is equals to S. So we have one is this, another one is this, and one plane we have already here. So it is three POS possible here. So this depends upon that what is the atoms or groups attached to the terminal carbon, that is a double bonded carbon. Right, so these three conditions you must keep in mind. And when you have odd number of cumulines, okay, odd number of cumulines, so this also, because we always have a plane of symmetry, so in this case we have no optical activity for odd number of cumulines. So this question they have asked many times in the exam. I'll just sum up this, you must keep this in mind. Cumuline, if you have even number of cumulines like 2, 4, 6, 8 and so, even number of cumulines, right? Even number means even number of double bond. Okay. So in case of even number, the molecule is non-planar and it is optically active. Okay. Odd number, the molecule is planar, optically inactive. Okay. Then the second point, if they ask you the number of plane of symmetry, it depends upon what group is attached to the terminal carbon atom. Depending upon the group, I have given you the condition, we can have the given number of symmetry, plane of symmetry. Okay. So this cumulines is important as far as the exam is concerned, whether it is JE or KUI. Cumulines is important. You just need to know the optical activity of cumulines. Okay, that is important. Okay. Another one. This is unsaturated compound we have discussed. Another one is cyclo compounds. Okay, or cyclic compounds. So in cyclic compounds, what happens? Suppose if you have unsubstituted compound. Unsubstituted compound, I have already given you the example, suppose we have a cyclopropane, right? We have a cyclobutane, right? We have cyclopentane, any other example. All these unsubstituted compound always have the plane of symmetry. Like for this example, you see, we have a plane of symmetry here along this point, POS. We also have a plane of symmetry like this. I've already shown you these examples. Like this is a plane of symmetry possible, right? If you have cyclopentane, see this example, if you have cyclopentane, cyclopentane also has plane of symmetry, which is this one, cyclopentane POS. So all these are, excuse me, all these are the example of unsubstituted cyclic compound. So unsubstituted cyclic compound, there is no doubt about the plane of symmetry. But if you have substituted one, okay, for example, if you have this cyclopropane and we have chlorine here and H here present, unsubstituted compound is this one and substituted is this. So again, you see, you can consider a plane which passes through the substituted atom. Obviously, this one is not a plane of symmetry, chlorine, hydrogen. This one is also not, this one is also not, this one is also not. Anyway, you can find out, you won't get a plane of symmetry. But if you have a plane which passes through the substituted atom, you always get a plane of symmetry when a plane passes through the substituted atom here. Means this plane is the plane of symmetry we have. You cut the molecule like this horizontally, right? Half chlorine this side, half chlorine other side, and both are the mirror image of each other. Okay, so this is mono-substituted compound, right? This is the plane of symmetry we have. Okay, so in mono-substituted also, you take the plane which passes through the substituted atom, you will get the plane of symmetry over there. Okay, always will have a plane of symmetry. So it also won't show optical isomerism. This also won't show optical isomerism. So whenever we have a plane of symmetry, optical isomerism is not possible. Okay. Di substituted, you see. This is the one we have, right? So in this one and in this one, you see. And we'll talk about this one. Okay, and one more we'll discuss here. Okay, now you see easily here, this is the plane of symmetry we have. Okay, so we'll have this POS here. We do not have any plane of symmetry. If you can visualize this, you can try. You won't get any plane of symmetry here. In this one, we have a plane of symmetry along this line. Sorry, not like this. We'll have a vertical line, the plane of symmetry like this. Right, H, CH3, CH3, we have a plane of symmetry. Right, this one, it does not look like a plane of symmetry we have here, but when we have a plane which passes through the dye substituted atom here, which is, for example, if you think of this plane, right, this plane, if you think of, passes through like this if you cut. So here we have a plane of symmetry, okay, and this plane passes through both substituted atoms. Okay, so in this one we have a plane of symmetry. Correct? These are the few elements, few examples I have shown you by which you can understand the concept of symmetry, that is the plane of symmetry, right? A few more examples if I show you here. CS3, CS3, H and H. Okay, so first of all, here you see we have a plane of symmetry in this molecule which passes through like this. CS3, CS3, we have a plane of symmetry. Here also we have a plane of symmetry passes through like this. Okay, benzene, if you talk about plane of symmetry in benzene, right? We can have plane of symmetry through this carbon atom, 1, then 2, then 3, and with sides also, you see along the sides also we can have 3. And since it is planar, so along the plane we have, so total 7 POS is possible here. This question is important, benzene, the number of POS here. Total number of POS for benzene ring is 7. Okay. One last example here, that is cyclooctene. Cyclooctene can have two forms, cis and trans. So cis cyclooctene will have a plane of symmetry like this, right? We have POS in this, but trans cyclooctane won't have any plane of symmetry present in it, right? That's how we can understand about the plane of symmetry in this. Okay, so this is important to understand the uh, symmetrical concept, the concept of symmetry, in order to obtain the optical nature of any compound. Okay, now if you have saturated compound, for saturated compound, what we do? Let's discuss this with some example. Suppose I am taking the simplest molecule, CH4, right? So carbon has 4 hydrogen tetrahedrally arranged, and the 2 hydrogen is in the other plane like this. So this 2 in the plane of the paper. This is coming out of the plane. This is going into the plane. Okay, so the plane of symmetry, if you consider, obviously it is a non-planar molecule. Non-planar, but if you consider this atom, like this hydrogen, and this carbon, right? These three will be in a plane, right? So we'll have a plane like this for this three atom will be in a plane, and along this plane, we'll have a plane of symmetry here. This is the POS we have, plane of symmetry, mirror image we have like this. Okay, so we are taking two hydrogen at a time to gain one plane of symmetry. So what is the number of plane of symmetry we have? We can find out by mathematical tool 4C2, that would be 6. 6 plane of symmetry possible here. If you number these, these hydrogen atoms like 1, 2, 3, 4. So 1 can associate with 2, 1 can associate with 3, 1 can associate with 4. Okay, 2 can associate with 1, 2 can associate with 3, 2 can associate with 4, right? 3 can associate with 1, 3 can associate with 2, and 3 can associate with 3. Okay, these are the combination we have, possible combination, but this one we already count. These two are same. 1 3 and 3 1. See here, 1 3 and 3 1. This one and this one are already same, so we have 1 over here. So not 1, it would be 2. These two gives you 2. 2 3 and 3 2. This gives you 3. So 1 2 3, then 4 5 and 6. So we have plane of symmetry possible. 4C2 also you can calculate here. Right? So we have a plane of symmetry, hence it is not optically active. Okay. Suppose if you take an example of CH3Cl. H. So when you have CH3Cl, so obviously you have to take the third atom, which is chlorine here, in this plane, right? So this one, and this one, consider a plane with these three atoms here, and along this plane here, like this, we'll have a plane of symmetry, POS. So number of POS in this case would be, we have 3 at hydrogen it can associate with, which is 3C1, and that would be 3 plane of symmetry possible here. Okay, if you consider, we'll take the last example here, CHCl BRLI, this is another molecule we have. So its structure would be carbon HCl Br and I. So in this case, you see, whatever you think, you won't have any plane of symmetry because all the 4 atoms are different. sp3 hybridized carbon here, right? It is an sp3 hybridized carbon with all 4 atoms are different, and hence it is a chiral carbon. And since there is no POS for this, it is optically active compound. So this is what we have discussed for plane of symmetry. Okay, so I haven't gone into that depth till JEE advanced level. I haven't gone, but I think the basic idea I have given you for this, like how to identify the plane of symmetry, and you can do the questions based on these informations easily. Okay, so must revise this. And next class, we'll talk about the center of symmetry also. Thank you guys. Take care. Bye.